In this lesson, we are going to learn a procedure to actually quantify and be able to say with certainty that a difference observed between the row percentages of some categorical data actually is really a difference. So you won't have to rely on, oh, it's about 10% and that seems like there might be a difference. So we are going to look specifically at 2x2 tables, so categorical variables that have two types of categories in both directions, so to speak. So inferential statistics is something that uses sample evidence to infer something about the population rather than measuring the whole population. So this is inferential So, for example, inferring that smoking leads to higher cancer rates, something like that. And the procedure used in inferential statistics to determine whether two variables are related, this is called hypothesis testing. And notice that related means there's some kind of association between them. It does not mean that one thing causes the other. And statistical significance, we say a relationship has statistical significance if it's unlikely to have occurred by chance. So a relationship is statistically significant if it is unlikely to have occurred by chance. So, for example, in the Physicians' Health Study, more than 22,000 male physicians were randomly assigned to either take aspirin or a placebo over a 5-year period to see if taking aspirin would reduce the risk of a heart attack. Now, the rate of heart attacks was 9.42 per 1,000 physicians. So that's 9.42 over 1,000 times 100% to make it that's the ratio, which comes out to be 0.942% in the aspirin group, or 17.13 per 1,000 physicians, which comes out to be 1.73% in the placebo group. And, it might not seem like that big of a difference, like 0.942% versus 1.73%. But looking at these numbers, 9.42 versus 17.3, it seems like that might actually be a big difference. And this difference was found to be statistically significant, which means that a sample difference this large is unlikely to have occurred by chance. If there was no difference in heart attack rates between the groups. All right, now there's a procedure used to do this test, and it's called hypothesis testing. And so there are 5 steps for figuring out significance. So the first step is to state your null and alternative hypotheses. The typical notation for the null hypothesis is H with a 0. And that comes from the fact that the word for 0 in German is null. So that's why 0. And the null hypothesis is always that there is no difference between the groups. So you should make this specific to your context, but in general, it's going to be that the variables are not related in the population. For example, in the one about the physician's health study, it would be that there is no relationship between drug being taken and heart attack rate. The alternative hypothesis is that the variables are related. And what you're trying to do, you're trying to disprove the null which implies that this is what's going on. So the null hypothesis is the thing you're trying to knock down, and then the alternative is the thing that you accept instead. All right, step 2 is to find this thing called the chi-squared statistic. Now that looks like a sort of squiggly X with a squared. And this is used to determine, or used to estimate, the association between two variables. We'll put this in quotes, a large value indicates a strong relationship. And I put large in quotes because large depends a lot on the context. So the stuff that we're going to be looking at in this lesson is only 2x2 tables. And so in that case, large means bigger than or equal to 3.84, which most people would really not call a very large number. But when you start to look at tables that are like 2x10, then what is large enough will actually increase and become more like what you think is a large distribution. Next, we have this thing called the p-value of the chi-square test. And what this will answer is, what is the likelihood that the chi-square statistic would be this big or bigger if there is no relationship? So what is the likelihood, or what are the chances that the chi-square statistic would be this big or larger if there is no relationship? And these numbers are kind of like probabilities. So generally speaking here, for chi-squared you need it to be big, you need p-value to be small. And once again, small's in quotes, but in general the small threshold is kind of set as 0.05 for lots of things. So this means it's a low probability that the statistic that you observe is going to be this big or larger if there is no relationship, which means it's likely that there is a relationship. Okay, now the last steps 4 and 5 are to make and report a decision. So when the p-value is less than or equal to 0.05 or 5%, we say that the observed relationship in the sample is statistically significant. In this event, we reject the null hypothesis in favor of the alternative, and we infer that the two variables are related. Doesn't mean one causes the other, they're just related. When the p-value is greater than 0.05 or 5%, we say that the observed relationship is not statistically significant and we cannot reject the null hypothesis. One thing to note is that this does not mean the null hypothesis H0 is true. You actually never, ever, ever conclude that the null hypothesis is true. You just conclude that you can't reject it. So there's insufficient evidence to reject the null hypothesis. You just don't know. And for 2x2 contingency tables, the rule about p-values has an equivalent statement in terms of chi-square statistic. So remember that for p-values, being small is what you need, and for chi-squared you have to be big. So we declare statistical significance when the chi-square statistic is bigger than or equal to 3.84, and we cannot declare statistical significance when the chi-square value is less than 3.84. So for now, we're probably going to use the chi-square statistics a lot more than the p-values because you can compute those without having to actually use software. We'll spend more time a lot later in this class actually talking a lot about p-values. So for each of the following results, explain what conclusion can be made about the null hypothesis that there is no relationship between two variables that form a 2x2 contingency table. So the thing to remember here, you reject H0 if P is less than or equal to 0.05 or if chi-squared is bigger than or equal to 3.84. And in both of those cases, the relationship is statistically significant. My point here is that this condition being met and that condition being met are equivalent things. If your p-value is less than 0.05, your chi-squared value is bigger than 3.84. If your chi-squared is bigger than 3.84, your p-value is going to be less than 0.05. Okay, so suppose you found a p-value was 0.049. Can you reject the null hypothesis or do you fail to reject the null hypothesis? Well, since this thing is less than 0.05, we reject H0. Okay, if your p-value is 0.755, that's way, way, way bigger than 0.05, which means it's pretty likely you would observe a relationship that big or larger due to chance. And you never say you accept H0. We fail to reject H0. And if the chi-square statistic is 2.89, well, that's smaller than 3.84, as in it's not big enough. Also, we fail to reject H0. In a survey done in 2010, students in a statistics class were asked whether they favored or opposed banning the use of phones while driving. Of the 105 female students, 37 opposed the idea and 68 were in favor. And of the 83 male students, 46 opposed the idea and 36 were in favor. So write a null and alternative hypothesis about sex and the opinion about a ban on cell phone use while driving. So the null hypothesis is always that there is no relationship. So we'll say gender and opinion about a cell phone ban are not related. As in, being one gender doesn't make you any more likely to be in favor or opposed to that cell phone ban. And the alternative is just that that's not the variables are related. So gender and opinion about a cell phone ban are related. So for these data, the value of the chi-square statistic came out to be 7.659, and the p-value came out to be 0.006. So based on these results, state a conclusion about the two variables in the situation and explain how you came to this conclusion. Now that explanation can be one of two things. Either the chi-square statistic is big enough or the p-value is small enough. Okay, so as chi-squared is bigger than 3.84, we reject H0, and then this leads you to accept the alternative because the null hypothesis is false, and this means that we accept that there is a relationship between gender and opinion about a cell phone ban. There appears to be a relationship. Between gender and opinion about a cell phone ban. Now I chose to use the chi-square statistic. That's not the only way to do this. Instead of saying this, you could use the p-value. You could say as p is less than or equal to 0.05, and then the rest of it could be the same. And the p-value is in some ways more intuitive. The probability that the difference would be this large is just 0.006, which is a really, really, really low. And because that's so low, it means that there probably, the fact that you think there is no relationship is false. There probably has to be some kind of relationship going on. Now, let's also compute percentages of students who opposed and favored the cell phone ban to kind of confirm that there is a difference between these two subgroups. So first for the ladies. So the females who oppose the cell phone ban. So of the 105 female students, 37 opposed. So 37 out of 105. That comes out to be approximately 35.2%. And those in favor, 68 out of 105, which is about 64.8%. Versus the males, now the proportion of males who opposed the ban, so there were 46 out of 83, which is about 55.4%. And in favor were 37 out of 83, which is about 44.6%. So what we just found here would have been row percentages, depending on how we organized our data. But you see that for the females, 35% opposed versus the males about 55% opposed. There's a large difference there, about 20%. So that's why the conclusion that we had about, we rejected that null hypothesis, there is a relationship, seems to also be supported by this data. So you see that about 20% more women favor the cell phone ban. suggesting an actual difference. Between these subgroups. Now the question is how the heck do you find that chi-square statistic in the first place? What do you do? And it's not a very difficult procedure, so here we go. So you start by finding something called expected counts. And this is what you would expect would be in that table, in your sort of 2x2 table, if the null hypothesis were true. It tells you how those people would be distributed among the yes or no things if there really was no difference. So the way you find the expected count is you take the row total times the column total and divide that by the total n for the entire table. Now, one thing to keep in mind, and this is actually kind of important, don't round the expected counts to whole numbers. It is a standard practice to retain at least 2 digits. And if you are checking your expected counts with something like software, if you keep more digits, it's going to make your chi-squared more accurate. But for now, to just all be consistent, let's just keep 2 digits. And one useful property, the expected counts in each row and column total to the same as the observed numbers. So for example, like in your little table here, these numbers are going to be different, but this number, those totals, those are all going to be the same as they were in the original table. Okay, and then you use these expected values to find the value of the chi-square statistic. So the first thing you do is for each cell you find the expected values. Which, remember, you find using the row total times the column total divided by the total. And then, once you find those, you kind of compare them to the values that you observed. If they're very, very different than the values that you observed, then you're going to get a big chi-squared. So chi-squared is equal to that big old sum symbol of observed minus expected squared divided by expected. And this is over every single place in your table. And remember, that big sigma symbol just means add them all up. So for the first place, do observed minus expected squared divided by expected, and just keep going. Another thing here is that this whole dividing by expected business lets you sort of scale it to account for maybe if you're dealing with values that are very, very large or very, very small. It's a way of sort of standardizing things. And the reason that it's squared is because if it wasn't, otherwise differences that were negative would cancel out differences that were positive. Okay, so let's actually do this for that data about the cell phones. So first, write a two-way table of observed counts for sex and whether or not a participant was opposed. So let's do female, male as rows, and we'll do oppose and favor here. And we'll find totals as well. Now, actually, you could do this either way. If you put the male and female as columns and the oppose and favor as rows, it's fine. So the number of females who oppose the ban is 37. The number of females in favor was 68. We're told that they total to 105. And you can check that by adding as well. The number of male students who are opposed is 46. And there are 37 in favor. And there were 83 total there. We need to find the column totals as well. So 37 plus 46 is 83. And 68 plus 37 is 105. And then the total is given by 105 plus 83, which is 188. All right, so that is the two-way table of observed counts. Usually you're going to be given that, but this would be how you would organize the table if you were just given something in a paragraph form. Next, determine the two-way table of expected counts for these data. So remember that that's the whole row total times column total divided by the total. Okay, so we're just going to make a table again. So female, male, keeping the same organizational scheme. Oppose and in favor. Okay, so for female oppose, the row total there is 105. The column total is 83, divided by the total of 188, which comes out to be 46.36. So if that null hypothesis of no difference was true, you'd expect about 46.36 people that would fall in the female opposed category. For favor, the row total is 105. The column total is also 105, divided by 188. This gives us 58.64. And one way to check that you are right would be to actually total this row, and this row should still total to 105, which it definitely does. So for the male oppose, that row total is 83, column total also 83 over 188, that is 36.64. And for the male in favor, 83 times 105 over 188, which is 46.36. Okay, so there are our expected counts, and you can see that they're definitely different than what we actually saw in the table itself. Okay, show calculations verifying that the chi-square statistic is 7.659. So remember, chi-squared is the sum of observed minus expected squared over expected. And observed values come from your table, expected come from your table of expected counts. So for female oppose, there were 37 women in that category. The expected value was 46.36. And we square it and divide by 46.36. Next, moving over, female in favor, there were 68 that we observed. We expected 58.64 squared divided by 58.64. Now down to the male row. Male oppose, we observed 46. We expected to see 36.64 squared over 36.64. And then finally, male in favor, we observed 37. We expected to see 46.36 squared over 46.36. Okay, so there are the calculations for the chi-square statistic. Now you can punch this in a calculator all in one go. That's totally fine. I don't really need to see your intermediary work, and it's actually better if you don't because we're going to have some rounding error then. But just make sure that you put parentheses where I put parentheses here. And you come out with, if you punch this in a calculator, you should get 7.66465. So what you really should do is pause this video and make sure that you can punch the calculator and actually get that value. Now something that you should be a little bit like, about is that we were trying to show that the chi-squared value was this, and we got something that was a little bit different. So don't freak out. The reason that this happened is because of something called rounding error. And it turns out that rounding these expected values to even just 2 decimal places will give you a different value than if you, say, kept more digits. So this number, the 7.659, was probably found using software, and that software probably retained lots of digits in its calculations, or kept things as fractions maybe. So in some ways it'd be nice for me to see that you actually got a little bit different chi-squared, because it tells me that you actually punched that number into your calculator correctly. Alright, so let's actually carry out a test from the start. So this table contains data from the General Social Survey for the relationship between whether individuals smoked and whether they had ever divorced for respondents who had ever been married. So write null and alternative hypotheses for the 2 variables in these situations. So H naught is always that there is no difference, so there is no relationship between smoking and divorce rate. And the alternative will be that there is a relationship between smoking and a divorce rate. Also note that this relationship is non-directional. Like, you don't say that smoking and divorce rate occur at a higher rate than not. For now, we're just talking about there is a relationship, there is no relationship. Okay, calculate the value of the chi-square statistic. Okay, well, this is a big step, because finding the chi-square statistic means you have to first find the expected values. So first thing you should do here is get the expected values. Okay, so we're going to have the yes and the no, and then the yes and the no, and the yes and no right here, that's the yes, you, no, you smoked. Yes, no here is the yes, no, divorced. Okay, so row total, column total divided by total total. So row total is 485, column total is 612 over 1669, comes out to be 177.84. For the no, we have row total is 485, column total is 1057 over 1669, 307.16. All right, for the yes divorced, no smoke, row total is 1184 times 612 over 1669. That comes out to be 434.16. And for the no smoke and no divorced, that's 1184 times 1057 over 1669, which comes out to be 749.84. Okay, now to find the chi-squared. So that's the sum of observed minus expected divided by expected. So we observed 238 people who had smoked and had been divorced. Expected only 177.84 of them. Okay, then yes smoked, no divorced, we observed 247. Expected 307. Okay, for the yes divorced, no smoke, we observed 374. We expected 434.16. And then finally, for the no smoke and no divorce, we observed 810. We expected 749 divided by 749.84. And you should verify that this for yourself, but when you plug this into a calculator, you end up with chi-squared is about equal to 45.297. Holy moly, that's huge. So based on that chi-square statistic alone, you could at this stage say, well, that's bigger than my 3.84 threshold, and yes, I reject H0 and accept HA. Now, we haven't talked about this yet, but here's how you find p-values. So you can use statistical software, but I think that a lot of you probably have a little bit of familiarity with Excel, so I'm going to show you how to do it in Excel. So in Excel, what you do is you type in any cell, equals, type in chi-dist, so C-H-I-D-I-S-T, x, comma, df. Now what goes in for x is the chi-square statistic, and df is this variable called degrees of freedom, and that's found using number of rows minus 1 times number of columns minus 1. For us, this is always going to be 1 because we have 2 rows and 2 columns. Notice that this calculation doesn't include the total columns. It's just saying of the possibilities. Later in the class, we'll do chi-square statistics with things where there are more than 2 categories in either the row or the column or both. So what you type into Excel is equal chi-dist, and it doesn't matter if it's upper or lowercase, it's going to capitalize it for you. Comma, x is our chi-square statistic, which is 45.297, and type in 1 for the degrees of freedom. And because this chi-squared is so big, you should get something that's really, really small. You're going to effectively get that p is equal to 0. And I'm not sure if Excel will actually give you 0, but I think it might in this case. One more aside, if you get something like 5.3 e negative 6, that's the same thing as 5.3 times 10 to the negative 6. In that scientific notation, you take that 5.3, move the decimal back 6 spots, so 1, 2, 3, 4, 5, 6. So that's the corresponding decimal. So you may have to also do that, and this decimal is certainly small enough to reject H0. Okay, so is the result statistically significant? Explain how you know. So yes, the result is statistically significant, and you have 2 reasons. Because the chi-squared is bigger than or equal to 3.84, or you could say that the p-value is less than or equal to 0.05, but those 2 things are equivalent. In the context of this situation, write a conclusion. So we reject H0 in favor of HA, and that's not really in context yet, but we'll go there in a second. So we conclude that there is a relationship between smoking and divorce rate. Now, one thing to notice, I didn't say that smoking causes divorce. So note, we never said smoking causes divorce. It's just that there is a relationship. If you are a smoker, you're more likely to be divorced than if you're not. So, not that it's causal. Now that nothing was a test for statistical significance, we also should discuss some factors that influence it. So, in general, whether we can infer that an observed relationship represents the relationship in the whole population depends on two things. First of all, it depends on the strength, as in how different are those row percentages. And the second thing it's going to depend on is the sample size. I mean, for example, there was this example we had about the physicians and the health study, and there was something like less than a full % of difference between the groups, which wouldn't be very different in a small sample, but that was a huge sample of 22,000 people, in which case that was considered a significant relationship. So what is a relationship depends on both how big the relationship is and how big your sample is. So the strength of the observed relationship, this can be measured by looking at the differences in row percentages. Okay, and sample size. Here's a hypothetical example. Suppose we did the same study, but we have different sample sizes. Okay, so suppose this first one we have n equals 20, and this one we have n equals 200. And in our n equals 20, thing A happens 80% of the time. Thing B happens 20% of the time. We want to say, is this actually different? Well, when you work this out, assuming we have each, so group A, group B, we have yes, no, we'd have, say, 10 in each group, 10, 10. So we'd have 8 here, 2 there, 2 there, 8 there. If you did a chi-square statistic with this, you're going to end up with chi-squared equaling 1.978 with a corresponding p-value of 0.16. In both cases, you fail to reject H naught, even though there is a 60% difference between those groups. And the problem is that a 60% difference is not very unlikely if you only have 20 people. But if you had 200 and you observed the same difference, so that would put group A, group B, we'd have 100 and 100. And then we'd have 80, 20, 20, 80. With that, you're going to end up with a chi-squared statistic of 19.78 and a p-value of 8.7 times 10 to the negative 8th. It's a very, very small number. And the point is the same proportion, different sample size, completely different conclusion. So it is really good to have a reasonably sized sample, probably at least 30 in each of your sort of subgroup categories there. And there's also practical versus statistical significance. So sometimes you might find something that's statistically significant, meaning that you tested for a difference. But sometimes it doesn't even matter, it's not practical. So for example, suppose I told you, oh my goodness, the risk of plane crash has doubled. It's a statistically significant difference. And the thing is that when something is unlikely to happen in the first place, its risk doubling is not, or tripling even, might not even actually be of any practical significance if the baseline risk is low. So if the baseline risk is low, doubling doesn't increase the actual risk by much. Okay, so for example, a statistically significant relationship was found between hormone therapy and invasive breast cancer. There were 166 cases of invasive breast cancer out of 8,506 women taking hormones, and 124 cases of breast cancer out of 8,102 women taking the placebo. What is the relative risk of invasive breast cancer when taking hormones compared to taking a placebo? So for hormones, there were 166 women who had cancer out of 8,506, 0.0195. And for the placebo group, we have 124 out of 8,102, which is 0.0153. So that's 1.95% versus 1.53%. I mean, that doesn't seem like a huge difference, right? But when you compute the relative risk, that's equal to this risk for category 1, so 1.95% over 1.53%. You end up with 1.275. So this makes it look like, well, oh my goodness, taking hormones leads to an increased risk of breast cancer. And it looks like it does, but the effect is quite slight. So the baseline risk, or reporting, so that lets you see that the relative risk is slight. Not that big. So what is the baseline risk of invasive breast cancer, assuming the placebo group is representative of the relevant population of women? Well, that would be what we found above, which was 1.53%. So breast cancer occurs in 1.53% of women anyway. And explain why it's important to report the baseline risk found in Part B when reporting the relative risk found in A. And it's important to know when the baseline risk is small, as any improvements or gains may also be small and not worth the risk. And the final thing is, what happens if you can't reject H0? So what happens if you can't reject H0? What do you say? Well, what you say is that you fail to reject H0. Note that you never say H0 is true. That's just not how this works. And what this means, if you fail to reject H0, it means that your sample results are not strong enough to safely conclude that there is a relationship. The sample results are not strong enough to safely conclude that there is a relationship. And a p-value that's too large means the observed relationship is not unlikely. If the variables are not related. But the most important thing I want you to take away from this is the fact that you never, ever, ever say H naught is true. You just fail to reject it. So there's just insufficient evidence to conclude that there is a relationship. Sample results not strong enough to conclude that there is a relationship. At that stage, there may or may not be a relationship, and the point is that that could be because there actually isn't a relationship. So the options is that there may be no relationship. That's a possibility. It also may be that your sample size is too small. And if you had gotten a larger sample, then maybe you would have had a statistically significant relationship. So you just don't know. It's a good old IDK.